Hey, so how are you, everyone? I see. Well, many of you haven't commented yet, but I want to ask if you have already checked in. If not, here's the link, so please go to register to this session. Shruti XP says, hey. So I don't remember seeing your name yesterday on the session, but I want to know how many of you were on yesterday's session. I know it was late. It depends on your time zone, of course, but for me, it was late. So let's continue with this part two, right? Abhinav Malik says hi, hi. So to do a little recap of what we do yesterday, we well in session or in part one, sorry, uh, we define what reinforcement learning is. Remember the idea or the concept of what reinforcement learning is comes naturally, like we learn for this reward system as child, as human beings, as like in nature. And this happens the same, or when we try to educate animals, we when we try to domesticate evil plants, even plants or anything, we do this same approach. And well, the idea of this trying to being away on how we teach the computer. It was very old, but thanks to computing and the advancements on how we can process now many data, it's that we can now perform this. Um, well, the core idea of reinforcement learning, it is easy to understand, again because it's the same, how we learn as as how to say this, as part of the nature, um, but we have to define this on an algorithm way, um, and I say between that quotes. But we have to define some rules on this. And we identify that we have an agent and an environment, right? So in this case, the artificial intelligence is going to be the agent. Um, the agent performs actions on the environment or vice versa, right? So the environment could be limited by ourselves, by the scope, or environment as human beings, it's the whole world. But depending on the context, an environment could be a chess game. Um, in this case, for example, with yesterday we create a model or we code a model for an agent to learn how to play blackjack. So the environment, it can be a casino or the blackjack game, indeed. So these two parts has interaction in the agent environment cycle. The agent has a policy, which is the actions can take and communicate with the environment, and the environment gives rewards and observations to this agent. The rewards can be positive or negative rewards, so like a punishment for perform an incorrect action. And this cycle, it's like this. Let me share it again. Just give me a second. Oh, I need, give me another second. If you didn't realize before, I'm not on my current, on my normal setup. So now I don't have two monitors, so I need to share this in a different way. Okay, but here it is. So we have this, right? The one I was talking about, the agent environment cycle, and this agent has the policy to perform actions on the environment. The environment give rewards and observations to the agent. Yesterday we were talking about, like, in control theory, this could be understand as a closed loop. That's fine too. Markup chains, and well, there's a lot of things in nature that replies these kind of actions, right? Um, and the other things we mentioned yesterday, for completing this recap, was the other elements in the reference learning, which are the policy. Again, the policy can be understand as the agent's way of behavior of a given time. Uh, if we are playing a game, the game rules, for example. This is like the mapping of the precise states. Another great analogy for this could be the state machine. For example, if you're following that paradigm of programming, very used when you program a hardware, for example. So this mapping of the states, it's the policy, and the actions to be taken on the environment, it's that states. Then we have the reward. Again, this reward can be, you're seeing my screen, right? I just wanted to confirm. But yeah, I think you're seeing. Let me supervise the stream. Okay, nice. Uh, this reward defines the goal of the reinforcement. Remember, at simple words, what we want to do with reinforcement learning, it's trying to maximize the reward we earn every episode. So this reward signal, it's what the environment sends back to the agent. This number can be, again, a positive or negative, and the agent's objective is to maximize this reward. So a negative reward uh, rests from the total amount, to saying that way, and now the agent understand that it was a bad action, or I think that probably doesn't want to repeat again, right? So that's the reward signal. The value function, for another way, the other element, this value function specifies what is good in the long run. This, roughly speaking, it's the value of the state in the total amount of the reward the agent can expect to accumulate. Um, we were talking, for example, in contrast of the model. Uh, the, the model, it's the element in the reinforcement learning system that mimics the behavior of the environment, and at some points um, can predict the next state or the next episode. We want to have a trade-off between how sure we are of an action and whether to explore or not other possibilities. Because, for example, imagine again the maze example. You could turn right every time because for a reason that we programming this way. When we turn right, Yeah, I can see your screen. Thank you a lot, Shimari. Can we get swag if we do none of the challenges? I'm not sure of that, to be honest. Like, what are the swag? It's sent to all participants, all that checked in many streams or a specific number of streams. I don't know. You will have to ask on Discord for. Sorry. And I'm sure someone knows that and can help you with that. Yeah, returning with this example I was saying, for example, if we program that giving a right turn on the maze will be a reward, we can enter on a eternity loop, like the agent is going never to be out of the maze, but he's okay with, okay, I'm earning rewards every time I do this turn right, so I have no reasons to turn left this time or to go ahead or to move back, for example. I have left only three. What do you mean? Lessons. Oh, okay. Yeah, again, I'm not sure what the parameters are to send swag, but you could ask for that on Discord just to be sure, which I recommend you. And yes, these parameters help us to make the artificial intelligence to learn in a learning rate or in a way that will mimic the way we as humans or our living things, because again, animals do the same, other animals do the same, and that's it. That's just the whole idea um, of of reinforcement learning. So that's the summary of what we did yesterday in theoretical aspects. And in practical, we checked how to run an algorithm called Monte Carlo. This specific algorithm, because it was for a blackjack game, and Monte Carlo, it is an algorithm developed for game theory, exactly. And it is not that great. I mean, we see yesterday at the very end of the stream that the output come from this Monte Carlo algorithm was not that bad, but um, in comparison with what we could achieve, for example, with another algorithm that is Q-learning. Uh, very bad. And not that very bad, but I mean, why could we do Monte Carlo if we could do another ones? Well, it depends on the things you try to achieve. For some cases, Monte Carlo could work fine, and well, there are trade-offs, right? Again, like in everything. Uh, Coding the Monte Carlo algorithm, it's easier in comparison, for example, to the Q-learning one. And in this session, we are not going to take back the blackjack example. We are going to make another one, which I think you will probably find more interesting. That it's the racing card. So some of the examples we were talking about yesterday on how to apply reinforcement learning was autonomous vehicles. And in this case, I mean, I know this is not real life and you're not programming a Tesla, but in this case, you will be teaching a vehicle how to move autonomously on a racetrack, right? So I think that it's very interesting. Um, of course, in real life, you have to worry about many other things. I mean, the the difficulty of this increases a lot. In this case, we don't have to worry about a third dimension, for example, because this will be um, a two-dimension game. And let me start sharing what I'm referring to. And this is all in the gymnasium library. So um, you could check, or you can just Google gymnasium. I recommend you to write reinforcement learning, because if you don't, I mean, gymnasium it's very standard, so you could start receiving spam from local gyms where you are. But the gymnasium documentation at the page, it's gymnasium.farmama.org. So this is the link. Let me share it with you. Okay, nice. Here it is. And as we can see, yesterday we take advantage of at Toytex, which is the blackjack. We didn't do this animation. Um, to be honest, I couldn't figure out how to do this, but we complete and take action on this. And as I was saying yesterday, one of the most difficult parts of doing the reinforcement learning, it's an analogy with other types of machine learning. For example, the supervised learning. The difficult thing there, or one of the most difficult things there, it's try to collect the data and process it. And there, for example, the rule is garbage in, garbage out. So if we pass garbage data to our model, the model is going to return garbage. In this case, the difficult thing about reinforcement learning, or one of the most difficult things, it's the creating environments. This creation of the environment could be really, really hard. Um, what I'm trying to say here is that the the Gymnasium API, it's great because it's a project that provides all common environments we could do uh, for starting in reinforcement learning. So we have a very big list here. For example, for classic controls, the cardboard. If you remember your control classes, it is very common in model systems and in classic control theory to try to tackle this with a PID, for example, or with other most robust control um, models of control. But in this case, we can complete this with reinforcement learning using artificial intelligence. Step before that could be using fuzzy logic, trying to do this same. So this classic control provides a lot of things. This acro robot, it's to pendulum, but we could also here the simple pendulum, like we could make a PID control to try to have this on how to say this, on equilibrium. No, well, to don't move but being vertical. And well, these space states define already for us the action space, the observation space, and how we can import them. And a little description of how or what the problem is. And well, in this case, also the reward system, and they define episodes, which help us code a lot less And well, if you don't find an environment that fits your needs, you can always create your environment, or even download third-party environments. There are multiple reinforcement learning tools, like, for example, uh, MainGrid, Mac Agent 2, or this other, for example, Reignatium for robotics. We can open this other one. And well, if this is your field, you could easily, well, not that easily, but I mean the problem of having to modeling the six axis robot, for example, in MATLAB or as a matrix, because remember this is funny, but a robot can be defined as a combination of matrices. Well, gymnasium robotics help you to create that environment for you. Here, for example, they the maze example on how to solve these kind of things, to get fetch something, uh, these kind of actions of sliding, reaching, pushing, etc. What else? Well, this is a very specific environment. um, Couple have had cheat. This for trying to teach a robot how to walk, right? Uh, Hope for humanoid researchers walk to the. Imagine trying to teach a robot how to walk. I mean, that's very complicated, and well, the pain of having to model all that space, and even in a graphic way, well, this helped us a lot. So, returning to what we're doing right now, which is the car racing, here's the, oh, let me remove this from the stream. Here's the environment we're going to use. It's from Box to Dimension Car Racing. Also, we have the bipedal walker. Uh, Similar, but not very similar to the other one. And we also have the lunar lander. And if you want to have more fun, for example, you have plenty Atari environments, because well, these games were already made. No, so Video Cube, for example, if you remember Atari, how many of you played this uh, any time? I mean, I didn't play many of these, but I played Pac-Man, for example. Imagine playing against an artificial intelligence. You could program the next world champion of Pac-Man. Whoever we have, Mr. Doom, Mrs. Batman, Phoenix, Pitfall, Pong, Robot Tank. Which one's this? Oh, haven't heard of this. Air Raid. There's Alien. Oh, it's like Pac-Man. I thought it was like, maybe I'm thinking of this Asterix. This is the one. No, which one's the one? Asteroids, I know this, the triangle. Yeah, moving again rocks. But no, which one is the one where the aliens like form rows and let things down to you? Blackjack's the one we used. Casino. I don't know. Maybe Defender? No, not this one either. Well, Hangman. No, even Mario Bros. Wow. Whoa, whoa. Another funny game, sorry, another funny fact is that you could come and play them yourself. So you can use this also as a Atari simulator because you can run this for you to play Space Invaders. Yeah, yeah, definitely. Sorry, um, I'm a '70s baby, and Atari was our first video game system. Wow, that's really cool. So you could come here and play some of these games here again. Uh, Probably there are better simulators, but it is a possibility too. I definitely play Atari, but never solved a Rubik's Cube on it. Okay, yeah, I played Atari, but not all of these, like just the famous ones. Space Invaders, Asteroids. I remember playing the one with a card, Pac-Man, for example, Tetris. It is weird to, yeah, here it is, Tetris, of course. Skin, Space War. No, this is not. I see. Yeah, here, Space Invaders. I miss it for just the one position, but very funny, right? So returning to this two-dimension box, the car racing. Let's take a look to the environment. This environment of the contains general information about the environment. The description is the easiest control task to learn from pixels. It's a top-down racing environment. Generated task it's ran the generated track is random every episode. Remember, an episode starts and ends with the finish of the game. For example, an episode of a chess game will be not every move, but the whole game, right? So that will be the episode. Some indicators are shown at the bottom of the window, along with the state RGB buffer. From left to right, true speed for our ABS sensor, steering wheel position, and gyroscope. Um, so this is what they are talking about. The true speed, it's these numbers. For ABA sensor, it's the blue one. Green, it's steering wheel position, and gyroscope, it will be the red indicator here. You can see this is kind of blipping. I mean, the car is not moving that fast, so that's why you don't see that a lot. Huh. So if we want to play it yourself, rather fast for humans, we can type this Gymnasium Environments Box TD car racing .py if we have installed the Gymnasium. And remember, it's a powerful rear wheel drive car, so don't press the accelerator and turn at the same time. Action space, it consists of three actions. The zero action, it's steering. Minus one, it is full left, and plus one, it's full right. So these three actions are divided in groups, and there are float 32. The first, it is an array or a list of elements. This list consists on steering, turning left, or turning right. The second action will be braking, sorry, accelerating or giving the gas, and the third will be braking. If we want to do this on discrete ways, we can change for five actions, meaning instead of having a list in the first action, we'll have them completely aligned. And then we have an observation space of a top down 96 by 96 RGB image of the card and racetrack. The reward it's -1 every frame, and 1,000 divided of the number of n, I think, oh yeah, the number of tiles visit in the track every frame, and plus 1,000 divided by n for every track tile visit, where n is the total number of the tiles of the track. For example, if you have finished in 732 frames, your reward is 1,000 minus or divided in those kind of frames you visit. The steering states the car is rest in the center of the road. That will be the starting point. The episode termination finish all when all tiles are visited. When the car gives a turn on, the car also gets outside of the playfield, that it's far from the track, which in this case will receive minus 100 reward and die. I mean, terminate the episode. The arguments, it's the lap complete percent, which dictates the percentage of tiles that must be visited by the agent before a lap is considered complete. What tile? Remember, we can consider these pixels tiles. So if we set this lap complete percentage as 1 or 100%, meaning that this will be the starting point and this will be the ending point. For example, if we set it to be 0.2 or the 20%, just a small part of the track will be visited. Returning here, passing the domain randomized through makes the track or the backgrounds different on every reset, and passing continues to false sets the environment to use the discrete action space. That will be the 5 actions we mentioned before, being don't do nothing, turn left, turn right, gas, and brake. We can reset the arguments passing the option randomize, and it will change the color of the environment at the map, corresponding passing the options false. And an example of usage of this will be like that. Import GHW, we make the environment, we set through the domain randomize, then we reset the color schema by default, and then we pass the randomized colors here, for example. But this is just an example of the arguments of receiving. We will see the example of how to do this. And well, let's check the references for doing this. We can close this now. No, what happened? Maybe the dot. Yeah, much better. So this is a C++ tutorial on the top-down car physics. And this is to understand how this was built, like the environment. I remember a good clarification was to not press a turn where it was. It's a powerful rear-wheel drive car, so don't press the accelerator and turn at the same time. So we need to move with the same, sorry, we need to turn with the same movement we generated. So, and to take a deeper look on how this was built, this can come handy. But for the moment, we are not doing this, right? But again, here's the reference if you want to check it out later. So let me prepare my screen now to be sure. Another thing. What's the link? Look, very cool. Oh, what link you meaning? Sorry. uh, Never mind. I see the link above. Thank you. Oh yeah, I get it. You mean you asked for the link of Nation? Sorry, here it is. That's a stripe down Spake Hunter game. The OG Spake Hunter. We need guns and oil six too. Didn't know that game. Hey, MLH, what's happening? Okay, I wait for your comment. Meanwhile, let me prepare these other things to be shared. Okay, here it is. So here's the Solving Generation Card Racing with Reinforcement Learning by Michael Kudati. It was released on the future, apparently, because this has date of September 24. Um, and I don't know what currently time zone you're living, but I'm I'm in August 14 of 2024. So I don't know. I just find this very weird, but this will make this will make great for the content. I mean, we are seeing content of the future. Here's the introduction. Um, Well, I think it deserves the reading. So, in the ever evolving world of artificial intelligence, reinforcement learning stands out as the powerful method for teaching agents how to make decisions based on complex environments. We already covered this on the intriguing challenge of the real of reinforcement learning is J Nation's card racing environment, a continuous control task that requires agents to navigate a racetrack efficiently, and this is environment process unique challenges, including high dimensional observation space and need for precise control actions. In this blog, we dive in the exciting process of solving this card environment using three prominent reinforcement learning algorithms: the soft actor critic (SACT), the proximal policy optimization (PPO), and the deep Q network. This is the Q learning. Each of these algorithms has its own strengths and weakness, so making them ideal candidates for a comparative study. So this is like a really good paper to check a comparison between these three algorithms. We will explore the theoretical foundations of each algorithm and discuss the implementation and analyze their performances of a car racing environment. By the end of the journey, we will gain these insights and the notions that each approach and understand how they handle changes possessed by continuous action space and dynamic environments. whether you seasoned reinforced learning practitioner or a curious newcomer, like many of us are, this exploration promises to deepen your understanding on the reinforced learning and its application complex uncontrolled tasks. Let me see if you have any question this far. By the way, how's everyone feeling? It's last class today. I'm sad. Let me check what comes after me. We still have a mini event from Ray and Lai, a Gartic phone mini event. Then we have Cecilia with Chat GPT for X in Flask. That will be a really cool stream. That will be the last technical stream, and then it's just me again with a no like mini event. 10 p.m. ET time, 8 p.m. for me, and then after that, yeah, that will be all. And tomorrow closing ceremony. So yeah, you're right. I'm sad. Next level, how we be here before you know it. Yeah, actually, that it's completely true. We've just been traveled 2 weeks in the future. We already in the next global hack week. Yeah, come back next month and we can do this together again. Yeah, next time it's cloud, of course, and there are many things I want to share with you about cloud. Cecilia is doing the stream. Yeah, exactly. Excited. Thanks. So let's return to this. The kart racing version 2 environment engineering, it's a continuous constant track where the agent controls a kart on a procedural generation racetrack. I think we can skip this, we already covered. And well, let's explain the proximal policy optimization. And here is a great diagram to show that. Proximity policy optimization, it's an algorithm that simplifies the truth region optimization used in algorithms like the TRPO, and in particular known for the stability and robustness in the environments with continuous action space. In this case, remember that we can define the action space to be continuous or discrete. If we set it to be discrete or set it to be continuous, this could change the result of of, of of the training, because as it is mentioned, the PPO it is better known for working with continuous action space. The diagram shows that we start the actor critic PPO with the actor network on the action, on the environment. We have a sample memory, and this is something, for example, the Monte Carlo didn't have a memory, right? Well, not specifically that, but well, in this case, we have a memory. We set the policy with a probability radio, the current policy and the old policy, in sum with the state value. Remember, we have our BS function, and here we can indicate this is a closed loop on the value loss. Then we update the critic parameters via the gradient descendant, and we set it to the advent function. In sum with the probability radio, we have the PPO loss clipped, and this is for updating the policy parameters via the gradient ascent method in this case, and that's being set for the actor again to update the policy in lesser terms. So the implementation of this can be resumed in this simple part. We set gymnasium, we import the PPO model from stable baselines. Um, let's look at this for us to understand better. And stable baselines is a set of reliable implementations of reinforcement learning algorithms in PyTorch. So in this case, differently for what we done have done with the Monte Carlo one, we code the whole Monte Carlo one. In this case, we are going to use a library to use the algorithm, which is great, so that we can skip all of that hard work and well simply go with result. In this case, I see they have the algorithms. Uh, AC2, DDP, DQN, HER, PPO, SAC, T3. We are going to use make of SAC, PPO, and DQN. So let's start exploring them, right? Deep Q network builds on filtered Q iteration. That's on top of this other algorithm, and make use of different tricks to stabilize the learning with neural networks. It uses a reply buffer and a target network and a gradient clipping. Notes the original paper of this, it's in this link and for the reference. The current policies, the multiprocessing and gene spaces, mild, dict, discrete. An example can be done using this env gym make carpal 1 render more human model dqn verbose model learned log interval and mode save. Remove the demonstrate saving and landing and model. It's going to be load on dqn load dqn carpal. But this is for the carpal. Remember what the carpal was? The classic control. This is the carpal. Nice. So let's return. Results. Attacker gains. The complete learning cubes are available on the associated pull request. How to replicate the results. Clone the repos. And well, the whole documentation it's here. But now this is now we understand from this we just import the PPO, then we create the racing environment of gymnasium and make. We initialize this PPO model with this sentence. This I think should be in the other line. We train the model. In this case, it's going to be trained with well, a billion. One, two, three, one, two, three. Yeah, a million episodes. That's a lot. Save the model. We save the model to PPO car racing, and we see the performance. The results of this, they are declared. Uh, let's open the GitHub repository because there's more images. So for example, here has the table. The PPO model was with discrete, sorry, with continuous, with the continuous setup. The average reward was this. So in general terms, well, here the total training steps, it's different from what I report on the posts, but that's fine. I mean, with lesser training steps and lesser training time, the average reward is better. And for example, we can see here the motion, it's really good. In comparison, we haven't checked this one, but in comparison with the SAC, that it goes low and it doesn't turn satisfactorily, right? And thinking of this, for example, this was updated just 5 days ago, and we don't have the deep Q learning yet, and the table it's not full. So I'm thinking this probably it was like a preview, but it will be completely foolish and available on September 24th, 2 weeks from now. So you can come again later and check this to see the complete result. But now we have the soft actor critic with SAC. SAC is an off-policy algorithm that utilizes both entropy. Sorry, I know that we forgot to see the strength and weakness. So we will return to stack. For PPO, the strength is that it performs well with continuous action environments like this, due to its ability to adjust the policies incrementally, avoiding drastic changes that could destabilize the training. The weakness is that being an on-policy algorithm, PPO might require more data in comparison to what a method like the soft actor critic could require, meaning that it will take less sample efficient. Um, which is weird because we see the result on number on trainings was bigger with the SAC. But okay, SAC is an off policy now. No, the PPO in practice. Sorry, this efficiently balance the exploration and exploitation. We talk about this trade-off, and the clipping mechanism of the PPO algorithm prevents large policy updates, making it reliable choice for environments where the control needs to be smooth and steady. Um, so PPO comes perfectly for this type of scenario. In conclusion, now again the SAC. Now this time, SAC is an off-policy algorithm that utilizes both entropy maximization and the actor creating framework for promoting the exploration by encouraging the agent to act as randomly as possible while it learns. So, same from stable baseline tree, we import the SAC algorithm. We use it on the model on environment. We train it and we set it. Then the performance in the card, as we saw here, it's not that good. But let's see what the results are here. The strength and the weakness. For strengths, high SAC it's highly sample efficient, means requiring lesser data. We know that, making it suitable for environments like the car racing, where the actions are continuous and precise and the control is necessary. I don't know. I feel weird this strength because in in the real life, well, not real life, but in practical terms, this didn't act as expected. So it maybe has to do with the policy or how we set this, or maybe it required another training time. But no, I don't know. Feels weak. Feels weird. The weakness is the algorithm. It's more complex to implement and requires a careful tuning. In this case, maybe this was why the result is this wrong, particularly of the temperature parameter, which balance exploration and exploitation. In this case, you see how the car always goes to the right, 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 right. I mean, we have now exploitation in this case. So maybe we need to be careful in this particular scenario. SACT in practice in the car racing environment, SACT entropy driven exploration helps the agent discover a variety of strategies and adapt to change in the track, which is critical for navigating complex hand dimensional space. Another thing is that, for example, these are the same tracks, and that could be a great point. Um, In this case, we should need to test this PPO with different tracks to see if this model didn't overfit to this specific task, to this specific task, and for example, the environment it's supposed to change the track every every time, but I don't know. It's weird because they look very the same to me. Finally, the DeepQ network, it's a pioneer algorithm in the reinforcement learning domain, particularly effective in discrete action spaces. So that's why in this case, we need to make this a, a discrete one. This is not set here. The way we set it, remember, it's on this one, domain randomized true. No, sorry. Yeah, domain randomized. No, continuous, continuous, false. So I see it is not declared here. Maybe again this post needs to be updated. It is not finished yet. Um, we initialize the DQN and on baseline tree with the environment, and we train the model. The performance says strings DQN at simple and effective in environments with discrete actions with relatively lower computational demands. The weakness is that it's less suited for a continuous action space, like this one, but it has a discrete version, so no problem here. The need for discretion of actions can lead to computational policies and reduce the performance. This could be a thing, yeah, too. DQN in practice, while DQN has achieved success like games in Atari, its performance in car racing is limited due to environment's continuous nature. Modifications such as discretizing the action space or hybrid approaches are necessary, but often leads to less optimal results. Um, these are the same. So, in conclusion, for this car environment, which has a continuous space, the PPO and SAC are more efficient choices. I have my doubts with this SAC one, but SAC's simple, efficient, and strong performance in continuous environment makes it particular advantageous. On the other hand, the QN, although powerful and discrete action spaces, it's less suited for this environment due to inherent design limitations. In summary, understanding the strengths and weakness of any of these algorithms provides valuable insight into the applicability to complex tasks like this car racing. So it was a great summary, great conclusions. And what we have here, it is the repository. So I have prepared the notebooks to be running, and I put them to run some time ago. So let's see if they already are done. So let me return here and just see. I see there are some comments. I think this is the one I read. I will surely, June. I mean, you're talking about the Cecilia stream. Will these videos be saved or can be reviewed later? Yes, on YouTube. Exactly. Thanks, Malik. Um, Here's the link. Thank you so much, Sparky Circuit student, Major League Hacking slash streams. This also too. Thanks. The second YouTube link doesn't work. Um, okay, yeah, it's okay. It's the Sparky link. I'm glad I see you around everywhere, and it really looks like you're getting a lot from Global Hack Week. Yeah, that's cool, Malik. Hey Alberto, what is your best advice for a beginner in machine learning? Uh, I consider myself a beginner in machine learning, to be honest. Um, I think to say it somehow that many people doesn't understand what machine learning is like in the concepts. And they think of this as simple tools that we can apply or a workflow for resolving something. Um, and I don't know. I had the particular scenario or the particular advantage that in my university they had a PhD program where they teach this kind of stuff. I'm currently not enrolled, but I'm planning to after I graduate my major studies. Um, and that, having that in mind led me to approach these researchers, these students in their PhDs, and ask them a lot of things, ask them a lot of questions, and they give me resources to learn. Like for example, the book I mentioned yesterday, which I need to repeat the biography, of course, because this is another stream. I will do that. Just give me a second. Um, but again, I will share just a book. What you need to do is trying to be close to these people who has more knowledge in the field. Again, for me, it was this campus in the university because they are currently doing research on artificial intelligence, right? Uh, if you don't have something similar, it is completely fine. You can start doing tasks in Kaggle, joining competences, try to look for hackathons based on artificial intelligence, on machine learning, on things like that. And sure, there are many people sharing very interesting stuff on YouTube, on internet. I can say of a channel, for example, that I look because I don't currently. The way I learned this, it's with the books I'm going to share, and to be honest, googling a lot of stuff. So the problem is that once you first start, like in everything, you don't know what you need to learn exactly, but because of course you don't know what you don't know. Um, but once you have like the full idea or like a good idea of what the picture is, like you can say, okay, I don't know this, I don't know this, I don't know this, I don't know this. Why do I know? Well, okay, I know this little part, so to complement that, I can start learning the things around this, and you can start Googling them. So no simple resource, like there is no a YouTube channel that I have found that has every information that I needed, or not a simple author or beauty platform. I don't know, like a specific school for teaching artificial intelligence, but that's it. Like just have the whole picture and start asking yourself what you don't know. For example, in this case, the algorithms, you now know that these pages exist with the algorithms, and they share like the papers where these algorithms were developed. As you can see, a lot of math it's required. I think you have a mathematical background, not that strong. I mean, you don't have to be a mathematician, but you need to understand some of the mathematical language, for example, or what functions mean, like how you declare them and how they can be represented, and how you can translate them to to code in a programming language. um, like that. So let me share the link, for example, for this book I used as biography for this session. Um, the reference. The name is Reinforced Learning and Introduction. It's from Bart Sutton and no, sorry, Sutton R and Barto A. But yeah, this is the biography, and it is cool because you start reading this and then you go to another and then you go to another because they are referenced. But well, this can you can start with this. Nice thinking. Hey, thanks. Um, have there been any website resource that have been particularly helpful in that learning process? This book, this book, reinforced learning. Um, Kaggle, Kaggle, to be honest, and the ones with the machine learning. I mean, again, artificial intelligence. It's more than just machine learning, but I think the machine learning community is really cool. Um, for example, if you look for the TensorFlow, and now I'm currently watching more PyTorch because my friend Chucho told me it was really cool and better than TensorFlow. The thing is, PyTorch doesn't have a support for JavaScript, so that's why I started actually with TensorFlow. But seeing their pages, they have lots of demos, lots of um, papers, workshops, lots of webinars, lots of these community sharing on how they do things, and you can get a lot of inspiration there. And also, they have even Discord servers where you can share with people. Um, I haven't done that. Like I'm not in Discord server, but I have heard that they have a very active community. So you can also enter that. For example, this site helped me introduce the basic of Git. Oh, thanks a lot. Learning Git branch inc.js.org. That's amazing. Thanks for the resource. But yeah, this book helped me to understand many things. The pages of the frame, well, not the frameworks, the libraries. In this case, TensorFlow and PyTorch. What else? Um, there's a incredible YouTube channel that teaches not about machine learning specifically, but about a lot of the mathematical things that you should know for machine learning. Um, the other time, a hacker shared it. Let me look for it. It is like the icon. It's like an eye with half blue, no, like three quarters blue and a quarter brown. But I can't remember the name now. I'm looking for it. Give me a second, and I will share it because it is so beautiful. And it helps that we give time to the algorithm to finish running. Three blue, one brown. Exactly that. The the description is animate the math, and well, that animation are really, really good. Oh, thank you, Sparky. Yeah, exactly. Triple one brown. Sorry, I didn't see the comments before, but here's the link. You can check it, and it is terrific. Okay, so we should learn by Java or Python. Oh, I will say Python definitely. Um, yeah, Python. DM me on Discord. I have many books, PDFs. Oh, no, that's cool. Thanks for sharing them. Yeah, exactly, Python. Any good reason? Well, um, Python is very loved by the community. I'm not talking about, oh, Python has a better performance for this, or Python has a better language manager, or garbage collector, or things like in technical stuff. I don't want to compare them because I think they are, have different purposes. But Python, it's very loved by the community. It has a lot of support for if you want to do machine learning. All machine learning libraries are in Python. Well, rating for Python, they are built in C probably, um, but yeah, between those two, Python. Exactly. Python has the most mature AI ML libraries. That I cannot agree more with this. Thanks, Natalie. PDF copy of the Sutton book. Thanks for sharing. Plus, you don't have to set any env or use any IDE because you can use Collab. Yeah, Collab helps you to manage that or Replit. Yeah, exactly. Thanks. Yeah, you can use Replit too. Thanks again for all the great resources sharing here and for the questions. So let's continue to the collab. Oh my god, this hasn't finished running. Okay, no worries. I will share them and I will explain the code, and we can. You have the code. You can share. You can run them locally and wait 3 hours, and then you can check the results. Sorry for not prepare that on advance. Okay, but here are the codes. Here's the repo. I cloned the repo. So we have first the deep Q network, and I think I know now the reason that the output is not set yet, because I have a problem here running this. Um, the error says that the model does not support multiple env. It will require a single vectorized environment. Let's see if we can fix this. But first, let's take a look to the PPO one. First, you need the the Swig library. Then you can install Gymnasium box 2D, and the library we checked for the models is stable baseline 3. We import the record video from Gymnasium wrappers, PPO from the stabilized bird 3, and we import some other functions needed for this to run. Make vectorized environment, back frame stack, back video recorder, base callback, eval callback, evaluate the policy, and the vectorized transposed image. Many of them are used for us to see. Oh, so sorry, I wasn't sharing. It's too confused on only one screen. Yeah, you're so right. I'm so used to watch my stream, check it, and to be honest, if you want to stream at some point of your life, I will definitely recommend you to have a second monitor just to monitor yourself. Like I mostly use that monitor for that, to check that the stream it's cool, that the comments are I mean, I can check the comments and answer the questions uh, on time and etc. Well, okay. Sorry, sorry for just sharing this. I know I have. Yeah, yeah. Uh, so we were saying that we need to install Swift, we need to install Gnation and these kind of things. That's cool, and we need to import the libraries. This part, thanks. I realized this before going further, but because it's pretty straightforward, right? Like a normal work for workflow for anything we want to do in Python. Now, this is where we start checking some things. We print the versions. For example, I'm using currently a version 3 of Python, the Torch, the CUDA, SciPy, NumPy, Baseline, IP, Gymnasium. And this is important. Probably wondering why we are doing this. This is important because many of these libraries changes every time. So I've seen that, for example, the requirements file from Python, and this is my perspective, it's not that good. For example, for what we have in JavaScript, for example, with the package log, uh, that is simply amazing. Helps you keep track uh, of everything of your versions and libraries. Then we create the environment of the racing cart. In this case, we are doing the PPO, so continuous, it's fine. We print the observations size space and the action size space. This is from the library, so we are good with that, and we close the environment. Then we start doing, or we create the training environment. For that, we are going to use an environment called make vector environment. This is the function from stable baseline tree. This receives what we want to do, the car racing 2, number of environments. In this case, we pass 1. Then we create another environment with the backframe stack passing the previous environment. And number of stacks will be 4. This can change based on your configurations, don't worry. Then we need to create the elevation environment. We set something very similar, but finally we add another step, which is the transpose image function for creating this evaluation. Sorry, this probably it is a wrong thing. This should not be elevation, this should be evaluation. So the evaluation environment gives the event callback. The event callback says to us of the evaluation callback, and we need to pass the environment, a word to store the logs, the frequency, and the render, and the number of episodes to be evaluated. Then we initialize the model as we saw on the post. This is the same. We set the policy, we set the environment, and our rows to be 0. The model it's saved now, so we can start learning with total time steps of 100. Sorry. Oh, I forgot how to call this. Okay, don't worry. This number, the progress bar as true, and the callback will be the evaluation callback, the function we established before, right? So this is why we need it. Then we save the model as PPO car racing. Once we have this, we evaluate the policy with the model. and the environment and the number of episodes, same as the callback, and we save that on the mean reward and the started reward. So we print this finally, we close the environment and the evaluation environment. This is the training that hadn't been complete yet after 87 minutes. But we can see the logs that, for example, the evaluation number of time steps at 500, sorry, at 5,000, the episode reward in the mean of that, it's minus 55. Uh, we see this is learning because, for example, we are seeing the reward every episode after 5,000 episodes each time. We see this, it's increasing, minus 55, 5, minus 30, minus 29, minus 28, minus 13. Here it is up again, but again, it is normal to see go up and down, up and down, up and down. The thing is at the end, and I see this is going to take much time that I expected because we're on 35,000, and this supposed to be to 100,000. Yeah, so we're not even half of this. Whew. Okay, but don't worry. Once we have this, we create the and another thing, um, which is the make environment vectorized again. Save it on the environment. We vectorize the frame stack with the environment we created before, and again we transpose the image. We load the best model from the logs that we are creating. In this case, we can run this uh, best model. That's it. Yeah, we can load the best model path. The best model will be by the load of the algorithm past the best model path on the environment. And again, we can now evaluate the policy to print the masked model uh, of this. This is with the past run of like the how to say this um, the cache, like the cache information of what we run before. This is the best model of this. But the terrible thing here is that I cannot upload the video yet because this hasn't finished. So in this case, the content videos are not available, but we can expect for these same settings, mean reward of 347 values. Remember, the maximum reward was 1,000. So this is yeah, this could work. It's not that good, but this could work. And the movie it can show us the video. Then we can see the performance here. So we load again the evaluations. We extract the data, and this all is to plot this line for performance. The time step being the maximum of the 100,000 and the mean reward. This it's the average we get of the 300, and this is the line of how the behavior of these logs is. So this I know it is hard to train and it takes a lot of data, but at the sorry a lot of time, not a lot of data. But after this is done, the output should look very similar to, let me start presenting my screen again, and this time I won't forget to share, I swear. The output should look very similar to this. Nice. To this video in which where we can look the race car to be very, very good at driving at high velocity in comparison, for example, what which is doing the sack, right? So that's it. Let me return to the Visual Studio. So here we are. And well, that same can be presented with a SAC factor, the self-actor critic, the SAC algorithm. We import the same libraries, we use the same tools, and we set the versions of this. Then we create the same spaces to get the sizes of this. We create the vectorized environment, we create the evaluation environment. We do very the same of the model, we only change the, even for example here, this is the initialize of the SAC, not of the PPO. The model should be stored with the same policy, the environment, and the verbose parameters. We train the model with the same time steps. We pass the function of the callback, and we set the progress bar to true. In this case, training, it's not giving us a lot of information yet. Oh, for example, the system doesn't have apparently enough memory to store the complete replay buffer, which will require 200, more than 200 gigabytes. Actually, I'm going to stop this before my computer crashes. Yeah, no, I interrupt this on purpose. I probably need to run this on T4 on Colab better, better than my computer, and wait for a result. Uh, but well, after this, the same process needs to be done. I mean, for us to store the best model logs on the zip. Um, and well, here the evaluation video will be generated. Once we have the evaluation video generated, we can see the mass model of this. It is stored here. It doesn't learn anything. I mean, at this point, the the PPO model has already become better. Here, for example, the reward here it's very the same. Uh, like in this, the mean reward. Uh, yeah, the mean reward. So this is terrible performance in comparison to the PPO, but still inside results and still give us information that we need to change how we are applying this model or change some parameters here because this is not working how we could expect. And well, the DQN it is not currently working, so we could do many things here. One, wait until the author. Well, let me drink some water because I feel my throat. Okay, sorry. We could take a look at this as lovers of the open source and make a pull request to the author and saying like, "Hey, I was watching Alberto's stream and I saw your code, and I think this could be the the how to say this the the problem you may be facing, and this could be the solution." Blah blah blah. We can wait until September 1st to see if the post has been officially realized, like with the results and with the complete code and everything, or we can open an issue. I mean, we can do several things here, but to the time, I don't think we could have time to fix this because this won't be fixed in like less than 10 minutes. So I will try. I will like better. Remember, here's the link of the repo if you didn't see it. Oh, so check this. Keep an eye on this to see how it results. I know it's working in progress, so it is a good thing I found this because I found this really really interesting, and I wanted to share with you. So here on the repo, you can also find a link to the post, Finding Theta. You can follow on LinkedIn. And well, Mikhail Kutlati is the author of this. Um, and you can find here more other cool tutorials. For example, this same comparison on the PPO, SAC, and DQN, but performing on the lunar lander, and just the lunar lander with DQN. So that's a way on how you continue your journey. And well, it's 12 minutes. So I would like to answer some questions if you have. If no, you can take a break. It's been a really, really long week. I know. Same for me. I mean, I give 7 streams this Global Hack Week, so uh, I need a break. I feel bad. I feel sad because this is ending, but another part of me, it's like, of course, like you needed this. You needed a break. You did a lot of amazing strings. Thank you, Shimori. I like you like it. I do this with a lot of heart for you to share what I know, the few things I know, and well, I just hope to share them in a correct way. Well, just come on, let me know if you have any question regarding the session regarding reinforcement learning with in general with machine learning or artificial intelligence, in general with your career path, in general with programming. I don't know, like we could talk a lot of great stuff. Yeah. Uh, I don't know. I didn't realize. Oh yeah, you're meaning like this. I'll always learn so much from you. Thank you. Thank you so much. Same here. Thanks. So well, I don't want to make this longer. Thanks for being here. Thanks for staying with me during these streams. I hope to see you back for Global Hack Week next month at Cloud One. And well, that's not the end of this. Still have two more mini games coming. One I'll be running myself. The other one, I think it's no, I think I'm sure it will be Ryan. And there's Cecilia stream coming up. So keep an eye on Global Hack Week. Side note, it's amazing to me how much my background in psychology and research statistics are helpful for coding, especially in ML. Yeah, exactly. Actually, as remember, as another side note, remember I was talking about how I start connecting with these researchers in the research laboratory of my school. They created like a summer school for artificial intelligence, and I attended, and many students were how to say this, like students that come from neurology, neurologists. I think that's the word. Okay, but yeah, the people from a lot of psychologists, a lot of like medical students, like from the medical field, which I found very interesting. And yeah, exactly, for machine learning and artificial intelligence in general, these kind of science are very helpful. Actually, in the institute they call them cognitive computational science, something like that. You're a really nice teacher. Thank you so much. I hope to see you back your screen again. Oh yeah, no, yeah, you forgot these ones. Hope you will get your screen back again soon. No, actually I have my screen. The thing is that sometimes I need to move from my home to other places to keep these streams. I have some appointments to attend in other place in town, so that's why. But my screen is fine. That doesn't happen anything to my beautiful second monitor. Neuropsychology, neurobiology. Okay, that's that's cool. Wow, that's a cool term. I'm glad to know it about. Yeah, the cognitive computer science. I don't think if that's like a thing in everywhere or just like in this research institute of my school, but it was created not that much time ago. It was created that specific lab. It was created, I think, 5 years or 3 years from now. So really new. It's still cool. Yeah, hope to see more of that in other centers around the world that are doing research. But yeah, it has been a beautiful side note. Thank you again, and this is bye for now. See you if you want to join me for the no like meet again at the end of the day, and if no, we'll see you on the next Global Hack Week. Thanks a lot, and put to run your collabs so you'll have the results in 2 or 3 hours. Appreciate it, Alberto. Yeah, bye bye.